All of our missions are complete, and we have trained hard to learn about electrochemical voltaic cells and its applications. Now it's time to focus on the other type of electrochemical cell, that is electrolytic cells. To do this, we must take what we know and use it for the Chunin exams. This means new information and battles/examples are ahead. Now our final mission is to learn about electrolytic cells, pass the 3 Chunin exam battles, and come back to the Hidden Chemistry Village as Chunin Ninja. That means we're going to be starting out in our Hidden Chemistry Village and traveling all the way to the land of Earth to get to the Hidden Electrolytic Village. This is considered a difficult task as it includes layering what we know and getting brand new information to make further connections. But we didn't come this far for nothing. We know it's our chemical ninja way to never give up, folks. So let's get to the land of Earth and get this exam started. Welcome to the Hidden Electrolytic Village, the site of the first test of the Chunin exams. Now for the Chunin exams, will we always be given instructions to learn and then battle in the arenas for answers to various problems. So for this test, Mew, the second Tsuchikage of the village and a powerful ninja and jutsu creator, will help us orient for this task. We're going to be learning about electrolytic cells, their operation, and parts of electrolysis. Mew then begins. We know a voltaic cell generates electrical energy from spontaneous reaction. Well, an electrolytic cell is going to require external electrical energy to drive a non-spontaneous redox reaction. So let's see how an electrolytic cell operates by constructing one from a voltaic cell. So let's consider a tin copper voltaic cell. Well, the tin anode will gradually be oxidized to tin 2+ ions, which enter the electrolyte. And the copper 2+ ions will gradually be reduced and play out on the copper cathode because the cell reaction is spontaneous, going from left to right in this direction. For this voltaic cell, we can then write our 2 half reactions. So we have tin losing 2 electrons and we have copper gaining 2 electrons. We are going to add these 2 half reactions together to get an overall reaction with a standard cell potential that is going to be 0.48 volts that are going to be generated. Okay. And also the standard free energy here is going to be negative 93 kilojoules. And this shows that this is a spontaneous process. Therefore, if we were to reverse this overall reaction, we have a non-spontaneous process. And we know a non-spontaneous process cannot happen on its own. But we can make it happen by supplying an electrical potential greater than the standard cell potential from an external source. So the standard cell potential for this spontaneous voltaic cell reaction was 0.48 volts. If we want to drive the non-spontaneous version of it for the electrolytic cell, we need to make sure we have a standard cell potential that is greater than 0.48 volts. Once you do have an external source that is greater than 0.48 volts, this is going to turn a voltaic cell to an electrolytic cell. Thus, the anode is going to become a cathode, and the cathode is going to become an anode. So in an electrolytic cell, as in a voltaic cell, oxidation takes place at the anode. So here we're going to have copper losing electrodes at the anode, and we're going to have tin gaining electrodes at the cathode. Note, however, that the direction of the electron flow and the signs of electrodes are reversed. So the anode here is going to be positive, whereas the cathode is negative in an electrolytic cell. And as you can see, the flow of electrons is going from right to left in an electrolytic cell. For an electrolytic cell, we still can go ahead and add the half reactions together and get an overall reaction. Now, the standard cell potential is going to be negative 0.48 volts to verify that this is a non-spontaneous process, and our standard free energy should be positive 93 kilojoules to again signify that this is non-spontaneous. To really understand the differences between voltaic and electrolytic cells, we focus on the cause of electron flow. So in a voltaic cell, electrons are generated in the anode, so it is negative, and they are removed from the cathode, so it is positive. But in an electrolytic cell, an external power source is going to supply electrons to the cathode, so it is negative, and removes them from the anode, so it is positive. Now, having explored the distinctions between electrolytic and voltaic cells, Mu wants to go further and discuss the connection between electrolytic cells and the discharge and recharge processes of the secondary lead-acid battery. Mu states, a rechargeable battery is a voltaic cell when it is discharging and an electrolytic cell when it is recharging. Let's go ahead and compare these two functions in a lead-acid car battery. So this graphic here is going to show the reactions in a car battery when they are running as a voltaic cell or discharging, and when they are running as an electrolytic cell or recharging. We have two electrodes here, electrode 1, which is going to signify negative, and electrode 2, which is going to signify the positive. In the discharge mode for a voltaic cell, oxidation is going to occur at electrode 1, thus making this the negative electrode, and the positive electrode will be the cathode. In recharge mode for an electrolytic cell, an input of electrical energy causes a negative electrode at electrode number 1. This is going to make the reduction at the cathode negative. And of course, the anode is therefore going to be a positive electrode here. So we can end up comparing our overall understanding of voltaic and electrolytic cells in a convenient little table. And this table is going to help us connect cell type, spontaneity, and of course, the signs of the electrodes here. So we have two electrochemical cell types. We have voltaic and electrolytic. Now, voltaic we know is going to be spontaneous, so delta G is going to be less than 0, and our non-standard cell potential should be greater than 0. Okay, so that is our voltaic cells there. We're still going to have our electrodes be an anode and the cathode, and of course, the anode is going to be oxidation at a voltaic cell, and the sign is negative. And for the cathode is going to be reduction at the electrode, and the sign is going to be positive for a voltaic cell. And of course, we see the opposite for an electrolytic cell. Our delta G is going to be greater than 0. Our standard cell or non-standard cell potential is going to be less than 0. We see the opposite here. Okay, we know that our electrodes are still going to be the anode and cathode, but we do have a flip in sign. So at the anode, we're still going to have oxidation occur, but the sign is going to be positive. And at the cathode, we're still going to have reduction occur, but now the sign is going to be negative. Mu now wants to delve into the fascinating realm of electrolysis and explore its applications in pure and mixed molten salts. See you there. So let's understand electrolysis. Electrolysis is the splitting or lysing of a substance by the input of an electrical energy. So lysis means splitting, and we know electrons coming from electrical energy, and so that's how we get electrolysis. So electrolytic cells are going to use electrolyte solutions such as molten salts or aqueous solutions to enable electrolysis. So we want to first prepare the electrolyte solution, and then we're going to add electrolytic electrodes, and therefore that's going to allow the cations and anions within the solution to move toward their opposite signed electrodes. So the cations are going to move toward the negative cathode, and the anions are going to move toward the positive anode for the electrolytic cell. This is going to facilitate the separation of ions and the production of the desired products at each of the electrodes. Now, this process is commonly used to decompose compounds into elements like chlorine, aluminum, copper, and others. Now, the entire journey began with the exploration of water electrolysis, and that is an historic process dating back to the 1800s and remains a crucial method for producing ultra-high purity hydrogen and oxygen gases. Now, in an electrolytic cells, the electrolyte can be water, it can be a pure compound, such as molten salt or a mixture of molten salts, and it also can be an aqueous solution. No matter what, the resulting products are going to depend on the atomic properties and, of course, various other factors. Mu emphasizes that he will focus on electrolysis of pure molten salts and mixed molten salt. So a molten salt is a type of ionic compound that is in a liquid state at very elevated temperatures. So in molten salts, you have cations and anions that are free to move, creating a conductive liquid. For the electrolysis of pure molten salts, we can predict the products of its electrolysis, and it's going to be very straightforward. Simply the cation will be reduced and the anion will be oxidized, okay? So the electrolyte is going to be the molten salt itself, and the ions are attracted by the oppositely charged electrodes to produce the product that we desire. So let's consider the electrolysis of the molten calcium chloride. So we know that calcium chloride is going to be CaCl2. And so we have two half reactions. We have 2 Cl minus forming CO2 gas, and of course, releasing 2 electrons, which means it's going to be oxidation at the anode. And of course, we have calcium, which is going to gain 2 electrons to form calcium solid, and it's going to be reduction at the cathode. And then the overall reaction is going to be our calcium liquid plus our chlorine, which is going to be liquid to form our calcium solid and our chlorine gas. So as you can see from this molten salt, we're able to produce our calcium solid. And calcium is prepared industrially this way, and of course several other active metals like sodium, magnesium, and a lot of halogens as well. And just to reiterate, for the electrolysis of pure molten salts, like we see here with CaCl2, we can simply use our standard cell potential or standard half cell potential values to figure out which one is the cathode and anode, and everything again is straightforward. Now, Mu wants to focus on electrolysis of mixed molten salt. Now, the overall process is still going to be the same, but the difference is the electrolyte is going to be a mixture of molten salts versus just one single molten salt. And this is actually what happens more commonly. You usually see a mixture of molten salts over the pure one. In other words, more typically, the electrolyte is a mixture of molten salts being electrolyzed to obtain one of the metals. So the question becomes, well, how can we tell which species will react at the electrode if we have a mixture of them? Well, the general rule is that the more easily reduced species is reduced at the cathode, and the more easily oxidized species is going to be oxidized at the anode. In other words, the stronger oxidizing agent is reduced at the cathode, and the stronger reducing agent is oxidized at the anode. But when it comes to mixed molten salts, we are actually confronted with another challenge. We cannot use these standard half cell potential values. And we really can't use these standard half cell values to assess the strength of oxidizing and reducing agents, as they really only relate to aqueous ions under standard conditions. And with a mixed molten salt, when you have multiple ions that are going to be moving around, it becomes more difficult. So we have to use another predictive approach, and that is going to be using our periodic table trends. Yes, that means we're going back to our Chem 101 scrolls to understand the trends for electronegativity and ionization energy. And that's going to be able to help us understand mixed molten salts and which one can be more reduced and which one can be more oxidized. With these trends, we find that the higher ionization energy and metals indicate a stronger oxidizing agent. So they tend to be reduced at the cathode. While you have a lower electronegativity in nonmetals is going to suggest a stronger reducing agent, meaning it's going to be oxidized at the anode. In summary, in molten salt mixtures, the cation with the higher ionization energy is going to be reduced at the cathode, and the anion with the lower electronegativity is going to be oxidized at the anode. And of course, you can go back to 101 and remember these trends, and we are going to increase ionization energy as we go across the periodic table and as we go up a group. We also are going to increase electronegativity as we go across the periodic table and as we go up a group, and then vice versa for the lower amounts. That sums up the first test information. Now we must use what we know about electrolysis to prepare for battle. Welcome to our first battle to test our current understanding from Tsuchikage Mu. We have Sakura versus Ino. Now, Sakura is a part of Team 7, so our loyalty is going to lie there. We must predict the electrolysis products of a molten salt mixture. This question states, a chemical engineer melts a naturally occurring mixture of NaBr and MgCl2 and decomposes it in an electrolytic cell. Predict the substance formed at each electrode and write balanced half reactions and the overall cell reaction. So we know we're dealing with a mixture of molten salts, and we need to determine which metal and non-metal will form more easily at those electrodes. So we're going to take the compounds that are given, and we're going to split them into their cations and anions. We can then list the ions as oxidizing or reducing agent. And then we're going to use our periodic table and the trends from our periodic table to go ahead and help us along. Now, if a metal holds its electrons more tightly than another, it has a higher ionization energy, and its cations will gain electrons more easily. Okay, and it will, of course, will be a stronger oxidizing agent. Now, if a non-metal is going to hold its electrons less tightly than another, it has a lower electronegativity, and its anion will lose electrons more easily, and it will be the reducing agent. So let's go ahead and start there. All right, so I have my two compounds, NaBr and MgCl2. I'm going to go ahead and get the cations and anions for each of them. So this is Na plus and Br minus, and this is Mg2 plus and 2Cl minus. Then I'm going to take my trends. I know that if I have a high ionization energy, I'm going to have a strong oxidizing agent, and it's going to be at the cathode. If I have a lower electronegativity, I'm going to have a strong reducing agent, and they'll be at the anode. So what I need to do is look at all of my cations and group them together, and all of my anions and group them together, because this is a mixture. If this was simply a pure salt, then it'll just be the one cation and the one anion. But because it's a mixture, we have to consolidate all cations and all anions. So here we're going to have our Na plus and our Mg2 plus, and these are all of our possible oxidizing agents. And here we have our Br minus and our Cl minus, and this is all of our possible reducing agents. Our goal is to predict the substance that is going to form at each electrode. So here we're going to figure out which one's going to form at the cathode, and here we're going to figure out which one is going to form at the anode. So what do? We focus on ionization energy here. As we go across the periodic table and as we go up a group, we're going to increase ionization energy. We're dealing with sodium and magnesium. As you can see, magnesium is going to have a higher ionization energy, so magnesium 2+ is going to form at the cathode. If it's forming at the cathode, that means magnesium 2+, going to be liquid form, is going to gain 2 electrons to form magnesium liquid, for example. Okay? And then next we have our anions, the Br- and Cl-, and this is all based on electronegativity. So the lower electronegativity is going to quote unquote win here, okay? So we have our Br- and we have our Cl-. As you can see, Br- is going to be lower. When we go down a group, we are going to decrease electronegativity. So then our Br- is going to be our anion for oxidation that forms at the anode. So we can get our 2 Br-, that's going to be a liquid. It's going to give us Br2 gaseous plus 2 electrons because we are losing electrons for oxidation. Now, sometimes these half reactions will be given, most times they will not. For bromine, you should understand that bromine naturally is going to exist as a diatomic, so it's Br2. So if I'm giving one single bromine ion, I know I'm going to need 2 of them in order to form Br2, and that means a loss of 2 electrons. Because I already know this is oxidation, then that's how I'm able to write this overall half reaction. For magnesium, we know we are dealing with reduction or gain of electrons. So we have Mg2+, and it's going to have to gain 2 electrons to get regular old magnesium here. And so that's how it's able to form these half reactions. Now, some of the smaller details, like knowing that magnesium is in liquid form or bromine is in liquid form here and then a gaseous form here, those details we might not have to know as far as understanding that, but you still should know how to be able to at least write out the overall half reaction. And so we have successfully figured out which substance is going to be formed at each electrode, and we have written out the overall balanced half reactions here. So we have the magnesium, and then we have the bromine. All we need to do is add these half reactions together to get the overall cell reaction. All right, so I take my Mg2+ plus 2 electrons, forming Mg liquid, and then I have my 2 Br- and then Br2 plus 2 electrons here. Now, because we are talking about molten salt, that also makes it easier to understand that the magnesium would be in liquid form. Now, again, we already have our electrons balanced, so we can get rid of the 2 electrons on either side, and we're left with the overall cell reaction as Mg2 plus liquid plus 2 Br- liquid is going to give Mg liquid plus Br2 gas. And so that is our final answer here. So that's going to be 3 different portions of this question that you need to answer. Figure out which one's going to be at the electrode, get the half reactions, add them together, and get the overall reactions, folks. Okay, the first test is over. Both Sakura and Ino answered the question at the same time. So no clear winner, and they both passed. Let's get to the second Chunin exam, folks.